100%. But other nuclides, chlorine, sodium, phosphorus, they're all high. Why do you think they're high? Chlorine, sodium, phosphorus. Why are they high? Why do you have high absorption in your gut? As well. Yeah, we all need those elements to live. So we absorb them to a high extent because we need them. So if you have a contaminant that behaves like a major nutrient, you have a problem, because as is cesium, what's cesium an analogue of that is a major nutrient? You can't answer. Okay? What does cesium behave like that's a major nutrient? Come on, guys. Potassium. Yeah. Potassium is a major nutrient. Cesium is an analogue of potassium. That's why we have a problem with cesium. Okay. Next question. Strontium. Again, quite high. Not as high as these, but nevertheless quite high. Analogue of... What's strontium an analogue of? What type? Where is it in the periodic table? Oh, it's dropped. No, it's okay. Can you not hear me? You can hear me? Yes, no?
Yes, okay.
No, the guys at the back. It's okay? It's okay. Okay, come on guys. What are the alkali metals? Calcium. Yep. Strontium is an analogue, a good, very strong analogue of calcium. Whereas, if we get down to these guys, plutonium and americium, would we be that worried about animals eating plutonium on a pasture? Would that worry you? This is maybe a bit too tough. The answer is that the absorption would be quite low. But what you should remember about plutonium and americium is that they are alpha emitters. Okay. So they are relatively radiotoxic. So you need much smaller quantities of plutonium for toxicity than you do of a beta or gamma. So we wouldn't expect much plutonium and americium in the body of a ruminant, but the animal itself, if it's ingesting vegetation with plutonium in it, will be getting a dose in the gut from the plutonium. And plutonium tends to accumulate in liver and bone. So if you have animals outside, there's a plutonium accident, then you would specifically look at the contamination levels in liver and bone. Yeah. But lower levels of plutonium are as important as higher levels of cesium, just in terms of the toxicity. But fortunately, no, they don't zip into meat and milk. They're very, very low levels in meat and milk. Okay. One complication with cesium, in the last slide, I showed you just one number, which is close to 100%. But one complication with cesium is that the absorption of cesium varies depending on the type of cesium. So if you have cesium absorbed to organic soil or ravengrass silt, this is estuary silt close to Sellafield. Most of the reprocessing waste from Sellafield, which is a reprocessing plant in the UK that takes Japanese waste, goes into the sea, and some of it comes back on the land, onto the estuary, and the sheep graze there. That cesium is quite strongly absorbed onto those sediments from the sea, and the absorption is quite low for the animals. Whereas if you have grass up here, cesium and bentonite here, hay, aqueous cesium, they're all quite high. Interestingly, the initial Chernobyl deposit on the surface of grass in Scotland, we were just about to do an experiment when we had the Chernobyl deposit in my country, and we found out about it at midday. We had our animals ready to do the experiment. We took out the institute staff to a field and we cut the grass straight away. So we were able to look at the particles on the surface of the grass. Just right time, right place, animals in place. And that initial deposit was less available than when it's taken up, the cesium is taken up into the plant. So in the early phase of an accident, you could have the cesium in a form where if it's intercepted in the emergency phase, it might have a different bioavailability and a different absorption to the phase when it's being taken up from the roots into the plant. Okay, as I said, the radionuclides tend to go into different target organs and be accumulated in different places in an animal. So here we have milk, we have iodine, cesium and strontium all go into milk quite readily. Meat, the main focus is cesium. Offal, this is what I mean by liver and kidney, brains, other things that people eat from an animal. You have a range of different things that go into that, including plutonium and americium, but also silver. Find silver in kidney. Cobalt 60 and ruthenium. For the thyroid, importantly, the thyroid accumulates iodine 131. And this is why we get thyroid cancer, is because we need quite a lot of iodine for our hormones that include iodine. So the thyroid actively takes iodine from the plasma. And in bone we have this different range of radionuclides. So depending on the radionuclide, you might be worried about different tissues in the animal. Yes? The thyroid? Yes. Yeah. The thyroid produces hormones which include iodine. A lot of them, thyroxine, which is really key for body functioning. And so it needs to make sure it takes up from the plasma enough to make those thyroxine molecules. So as I said, one of the key sources in the international community for the data that we use for this is TRS-472. TRS-472 is a summary document. It's intended to be easy to look and to read by everybody. TechDoc 1616 is more detailed. So it has more information in it. So if you're particularly interested in one thing or another, go to 1616 rather than 472. So how do we quantify transfer to animals? In the past, we would use this. So this is called a transfer coefficient, called FM. Don't ask me why. 1960s, some American somewhere. It's becquerels per kilogram fresh weight in milk divided by becquerel per kilogram per day. So it's how much an animal eats per day. What might be a problem with that if you're trying to quantify transfer? Why could that be a problem? Getting this number. If you've got an animal in the pasture, how much is it eating a day? How would you know how much it's eating per day? It can be done, but it's not easy. It's quite complex. It depends on the live weight, it depends on how active they are, it depends on if they're lactating or not, pregnant. It might depend on the quality of the forage in the pasture. So the uncertainty associated with that number can be quite high. The reason we started to use transfer coefficient in the first place is some scientists in America called Ward and Wicker, who are very well known for early animal work, looked at the variability in quantifying transfer to one herd in one pasture. And they found that if they looked at the daily intake, it was less variable, slightly less variable than if they looked at the becquerel per kilogram. So they said, this is what we should do, guys. We should use the transfer coefficient and do it by the daily intake. Whereas these days, and it's mostly at the instigation of myself and Nick Beresford, who you met yesterday, we have said we think we should go and use this, the becquerels per kilogram, and not the daily intake. Because in science, what you often get is one scientist will suggest a way of quantifying something, and then everybody behaves like a sheep in our country and just follows. You know, there's Walter Wicker out there, they're into, oh yeah, they're clever scientists, I'm going to follow them. And you don't think about it. You don't question it. You know, who am I to question Ward and Wicker? You know, they're very well known, well published scientists. How could I dare to say they were wrong? People don't think. They don't question. They don't say, is that really the best way to do this? Yeah. And the more eminent the person who suggested it, the less likely they are to question it. But if you can, of course, analyse data and see whether that's true. One problem you have if you compare data is how good is the data you're comparing. Okay? So this quotient is relatively easy, as long as the person who is reporting tells you everything that is being eaten by the animal and the quantities and the contamination level. You can calculate that fairly well. The number of people who report transfer coefficients in field data and have guessed how much an animal eats, not measured it. Sometimes they have a basis to that. Sometimes they look at the live weight of the animal, and of course the bigger an animal, the more it eats. So there are relationships in agricultural literature which will tell you how much an animal is eating. But instead, they might go to the predecessor of this, which was TRS 364. In TRS 364, Gabby Voigt, a colleague of Gerhard's at GSF, and myself, we took over from an American scientist called Ing, who had collated a lot of information at a very late stage in the process because he wasn't very well. And we reported in here what we thought was an average level of intake for a typical dairy cow. But nothing more than that. Just this could be an example of what you might use. In 472, we didn't report a number because we thought, no, this is going to vary tremendously with the livestock, you know, with the type of animal, the intensity of production. In Russia in the 1950s, when there was the Kushner accident, the average litre production of a cow was 10 litres. The production of a dairy cow in Western European countries, and probably here as well, is something like 25 to 30 litres. That greatly impacts on the productivity and the extent to which the nuclides might be into the milk. So it's very difficult to have confidence in some of the numbers. If it's a controlled experiment where people are actually measuring it, then you have a lot more confidence in the number. So this is just giving an example of trying to be critical about the numbers you use and looking at what's behind those numbers and whether they actually stand up to any thought about the process. So these are CR values. So this is the concentration in milk divided by the concentration in feed for a range of different elements. The numbers up here are the numbers of data we found in the literature for the different radionuclides or elements. So you can see which is very good, we have quite a lot of data for iodine and particularly cesium. So we have a reasonable degree of confidence in those numbers, but we know that the cesium number can vary if it's not root to plant uptake. But much of the time after the emergency phase, for instance, or in normal situations, it is soil to root uptake. And we have quite a lot of data for strontium, and the reason for that, of course, is that we have some good data after the Plutonium accident from the former Soviet Union countries, who published a lot of material, but for the first, until 1990, very little of that material was actually published in English, and that's because the accident was kept secret by the USSR. So there was no data published in the open literature on all the huge amount of research that was going on in the Urals at that time by USSR scientists. But now a lot of it is out and has been compiled by Sergei Fosenko, for instance, together with us. And then as we go down and we look at the other things that I've mentioned for the other nuclear accidents, we see that the number of data we have is really low. No. So we don't have a lot of values once you get away from the big three. Does that matter? Well, plutonium exercises everybody, because one of the reasons that you might be concerned about a radionuclide is not because of the dose that a person might get, it's because of concern about the radionuclide that the people might feel. And if you say plutonium, people are scared. People worry about it. No. And even though, hand on heart I can say I really don't think anybody is going to have a significant dose of plutonium in milk, I still think that we need to demonstrate and prove that that's the case to the public. So it's another example of where you might want to do experiments and get good data, not because you think it's an important contributor to someone's dose, but because you think people might be worried about it. So if I use that argument, I would say, 3 or 4 is not really that good, especially for polonium, which is relatively mobile. What we are also doing in the Medaria program, and in the first phase, is to actually look at the distribution of the data. So this is the transfer coefficient using the old method, and this is the concentration ratio, and this is cesium, iodine and strontium. So nowadays we can look at the distribution, we look at the distribution of the data as well. And one reason to look at the distribution of the data is when you're trying to set feeding limits. Because, in particular, you're interested in the high values. No. Should you use that value, or can you use that value? So looking at the distribution of the data, deciding on the confidence you have, or what value you actually want to use. Do you want to use the 95th percentile or not? You can now use the distribution of these data, and all these data have recently been published. Every single number underpinning these data we have just published. then the regulator can then look at that data, look at the data for the country, and make a decision and support that decision with open source information. So it's getting away from the idea that you might use the mean, and most of these data are normally distributed. But you would say, make a decision that we would use the 10th percentile or the 95th percentile, depending on what you want to do, and then be able to quote these numbers or compare them to your own country's numbers. And now I'm talking more generally. I mean, this is for cow milk, but it's a similar situation for any transfer value that might impact on a limit. It's thinking about what number you use and trying to provide information so that a regulator or a group of experts getting together, like they did for the EC limits, would have much more information to hand of a quantitative nature to be able to decide and justify transparently how they did it. And transparently is a really important word, because I went back to the European Commission when I was looking at the Japanese feeding limits and talking to Japanese MAF about how to set their values. I went back to the European Commission and said, how did you set that number for the feeding limits for Europe? I went back to DG 11, which did this in that day. They couldn't find how they did it. They had no documentation. They had a group of experts together that talked about it and decided on the numbers, but they could give me nothing which explained how they did it. It was probably there at some point. I'm sure it was, but they can't find it now. So transparency, I think, is really important, and looking at the distribution of data as well. And that's something that in the Madaria program we're trying to do, is to actually make this much more transparent and allow people to use these data on uncertainty, variability. So you can see here, this again is for cow milk, and what we can do is for the different elements. This is where for the elements we have a difference of 2 orders of magnitude, where the difference is greater than 2 orders of magnitude. So these are the elements where we have a great deal of variability. Now that might be because we have a lot of data and there is a natural amount of variability, or it might be because we have hardly any data, and the few data we have are very different. So there's different reasons why you might have a lot of variability. One thing that we've also developed in Madaria is, for many of the animal products, we have to give values, or try to give quantifier values for more than 30 elements. It's impossible. There just isn't the data for the transfer to different animal products for well, it's actually 50 to 60 elements in total for the ICRP list. So what we've been trying to do is develop methods to extrapolate. And because often you will see in literature, we didn't have a value for X, so we used the value for Y, because we think it's an analogue. Often not really looking at whether the data for the analogue truly is quite similar for anything which is quite close to the particular transfer that they're looking at. So what we did here is we took the fractional absorption numbers that we had, and we correlated them with the transfer coefficient. We've done it with the concentration ratio as well. And we actually found that there was quite a good correlation between the fractional absorption and what gets transferred into milk. Now, ICRP lists all the fractional absorption for all the elements that it needs to consider for man. So if we know this relationship, we can use the fractional absorption numbers of the ICRP for humans, and we can predict it in milk. So using extrapolation and relationships you can derive from literature can be used to fill in data gaps in a way which is actually using a process rather than just an assumption. One One of the things that's quite important, especially after accidents, is time. Things change with time. Contamination levels go down, hopefully. Not always, mostly. So we need to identify, obviously we know the physical half-life of a radionuclide, of an isotope. But we need to know the biological half-life. How fast from a contaminated animal does the radionuclide get removed from the animal in the feces and urine, usually? Ecological half-life, one takes account of physical decay and one doesn't. That's the only difference between them. And they are used in the environmental setting, so looking at what contamination level you might have in rice in the first harvest compared with 5 years later, for instance. So you actually look at these decay constants, and that's the way that we quantify it. So for instance, this is radiocesium in crops with time after Chernobyl, becquerels per kilogram per metre square. It's a potato, tuber, oats, barley and winter rice. So this is just an example of the types of data that we might collect. But the biological half-life in milk is very important, and it is quite fortunate that the half-life of many radionuclides in milk is about 1 to 3 days. So it's rapid. So it goes from very quickly. If you have a contaminated animal and you take that animal away from the contamination, the decontamination in the milk is rapid. It's very fast, which is good. For the animal products, the biological half-life varies quite a lot, and it's influenced by age and size. So the larger an animal, the longer the biological half-life. So a cow has a longer biological half-life than a goat. But in some cases, it's not that simple, because, for instance, strontium, analogue of calcium, quite a lot of strontium goes into the bone. And the bone releases calcium, and strontium. If you take an animal that's contaminated with strontium in its bone, and you put it on an uncontaminated area, you won't necessarily get a milk which is just from the current intake, because the strontium in the bone is released and contributes to the milk, because it goes into the plasma, and so some of it goes into the milk. So you'll get so if you have an animal which has been contaminated for quite a long time, and in pasture, say, for 6 months or 2 years, and then you take it away, the strontium that is there in the bone starts to come out and contributes to what's in milk. So these are long effective ecological half-lives for cesium. This is mushrooms, this is upland sheep in the UK, and this is potatoes. I mean, this is stylized, but it just gives you an idea that for mushrooms, some mushrooms you can have very little reduction with time. As in the Chernobyl area, there's still mushrooms with very high levels of contamination, even now. And in the UK. And in upland sheep, we have a gradual reduction, but we had restrictions on our sheep after the Chernobyl accident, that the farmers couldn't just sell the sheep, they had to decontaminate them first. We only stopped that. Okay, accident for Chernobyl happened in 1986. When do you think we stopped our sheep restrictions in England? Three years ago.
And 3 years ago, you mentioned?
Yeah, 2012.
One question is, does this include the decay or not?
It's effective.
Effective?
Yeah.
It's ecological plus decay?
Yeah. Yeah. But it's only really to illustrative purposes. Yeah. So even though in Western Europe we didn't get a lot of contamination from Chernobyl, the impact lasted for a long time. So we have, talking about the data and the reasons we might want better data, we have made, especially under these international programs that Gerhard was talking about, and EC projects in collaboration with the former Soviet Union countries, we've moved from a data to a data-only basis. So for 472, TRS 472, we only use data. In 364, which was the previous one published in 1994, we used assumptions and we used review data as well. Now it's only data, there's no assumptions in there. We on the animal side, we report concentration ratios as well as trend flow coefficients. So we allow people to use concentration ratios as well. We've added the gut absorption numbers. We've developed extrapolation methods if you don't know the value or if the value is not reported. And I think this is one of the most important things, is that we've greatly increased the transparency and the provenance of the numbers that we give. And by provenance, I mean, where does it come from? How is it justified? How did you get that number? Because often you'll see a table which will give you a number, and you'll say there were 57 data that contribute to that number. Well, which 57 data? Exactly which values? No. For the animals now, we have published a referee journal paper with a huge reference list, which tells you where every single number came from. And I think that's really important, so you can show the public exactly how this number has been derived, and they can decide for themselves whether they think that the number that is being used by the authorities is justified or not. There's some problems with it. Limited access to the individual data. We have done it for cow milk, we've done it for goat milk. We haven't done it yet for beef, we haven't done it for sheep milk, we haven't done it for sheep meat, we haven't done it for pork, we haven't done it for eggs. Why not? Because it's an awful lot of work. It's a huge amount of work. And those people that contribute to TRS 472 haven't just not got the time to do it. It's a very long, hard job. There are other reasons, like people do not necessarily want to just let everybody else have their own data set. No, we've spent much time and effort compiling, so some people are not very happy to give it away. So it varies. Often the people who put together 472 and the data in 472, if you approach them individually, they will let people have data. And I have done that on occasions before I published it with the animal data. What I once said no to was I had a German PhD who desperately needed all the cow milk data by next month because I have a PhD exam and I need to know all the data. And I told him to get lost. I mean, there are limits. No. Mostly I'm nice. But not when I'm told that I need all your data by next month. Yeah. So you have to be nice to the scientists and not make ridiculous requirements, and then you maybe get the data. Site specificity. Of course, the international data gives you a basis on which you might decide a number for your country. But it is always good to have site-specific data there that you can compare to that data to make sure there's nothing particularly different about your country or your particular animals. So it is definitely a good idea to have some site-specific values for your own country. Before the Fukushima Daiichi accident, there were relatively few data for animal products in Japan. There were no ruminant specialists working on radionuclides, none. There were no radioecologists who did any experimental work with agricultural animals. There were radioecologists who compiled the data on the contamination levels of radionuclides and nuclear weapons fallout. So Japan had data on the reduction with time during the nuclear weapons fallout period. And it could use that to estimate transfer by comparing it to the contamination level on the vegetation. But no specialists at all. And that was a problem. And I got an email from someone in Japan who knew someone who worked in my institute. And that's how they found me. It's not the best way to do that. It really is better to have some preparation so that even if you don't have specialists in your country, you know where they are or who you might go to. The first port of call, for my purposes, would be the IAEA to tell you who is there. The update of the documents 472-364 is less than one per decade. Which means, and one of the reasons for that is it's a huge amount of work. This brings together the international community to compile all these data, to put them all together, to discuss them, to QC them, and it's an enormous effort. So the rate at which they're updated, one per decade, it was 1994, and it was 2009, 2010 when TI 472 and 1616 TechDoc were released. So it's less than one a decade. So overall, I would say the take-home messages on this about data is there's a lot of data out there for some radionuclides. There's a lot less for many of them. The international sources, they're not a Bible. People who write them make mistakes. I make mistakes. So be sceptical, look at the data, decide whether it's right or not yourself, or go to someone and to discuss it with them. And in some cases, one value based on 15 data, where the underpinning data for that are all good quality data, might be better than another value with 80 data, whereas most of the data are pretty awful. So data quantity doesn't necessarily mean it's a better data point. In some cases, we report a lot of CR values, for different products. And we look at the data, say, for sheep milk, cow milk, goat milk. If you look at the transfer coefficient of them, they will be different because it's in the maths, and I don't have time to explain it, but they will be different. The CRs, again, because it doesn't take into account intake, should be the same. You can show mathematically that they should be the same. When we get enough data on CRs, because everybody now, most people nowadays do report CRs as well as FM. When we get enough data for CRs, if we can prove it for more elements, we can dispense with giving data tables for sheep milk, goat milk and cow milk. We just have one for milk. And that will help tremendously in the future. Site-specific data are important. And one big question that we're now looking in Madaria 2, which I think you really have to think about, is does the lack of data really matter? We have a lot of gaps in our data tables. But if that particular isotope is hardly ever released from a nuclear power facility, or hardly likely to be released in an accident, or is not important in radioactive waste disposal, or has a very low energy associated with it, so the dose you get from that isotope is not particularly important, it might be that you don't need data for that particular isotope. So it's very important to think about those things. If you assume a very, very high transfer, and you show, even if you assume a very high transfer, you get hardly any dose to the human, does it really matter? No. So what I'm saying is that we may have a lot of gaps, but quite a few of those gaps probably don't matter. And where we need to focus our attention on is where it does matter. And in some cases, I think today, we don't necessarily do that in a systematic way. We know cesium and iodine and strontium are important, but we don't systematically say, well, how much data do we need for cobalt, for instance, or how much data do we need for some of the other nuclides that have relatively high gut absorption? Do we need more data for that? Do we have sources for that? Are there legacy sites where we have those nuclides? So we need to think more systematically about it to actually identify where we have the gaps that actually matter. And I think that most of the gaps probably don't matter that much. Okay, 10-minute break.